So thanks everyone for coming. I'm very sorry that I couldn't be there in person. Unfortunately, this also means that I can't see who's in the room. So, I can't like on the fly adapt what I'm saying based on, my recognition of the faces who are there or not there. So this will be, a 1 hour introduction to quantum, kind of aimed towards cryptographers. And because it will be a 1 hour introduction to quantum, it will necessarily be very far from perfect and very sketchy, but hopefully it will at least kind of on average help prepare us for the upcoming talks in the workshop. Okay, so I'm going to just start right at the beginning and move pretty quickly. So let's start with the qubit, the quantum analog of the classical bit. So the valid states of a qubit are two-dimensional complex vectors, and the squares of the coefficients have to sum to 1. Okay, so complex vectors with 2 norm 1, and this this kind of funny notation, if you haven't seen it before, for now these sort of we're going to call this kets. And for now, you can just assume that it's some sort of indication that the object inside is a vector. I'm using it here for 0 and 1 as well. And here, these two, so these are vectors as well. And in fact, they're orthonormal vectors. So, the inner product, which I'm going to write like this, between these two vectors is 0, and they each have norm 1. And if you want to think about this in the maybe kind of high school way of thinking about vectors, column vectors, ket 0, you can think about as the 1, 0 vector, and ket 1 is 0, 1, and then ket alpha is, of course, this vector here. Okay, now what are the valid transformations for qubits? Well, they're going to just be linear operators which preserve this property of having norm 1. Okay, so and these are called, of course, unitary operators. So here's an equivalent formulation of what it means for a linear operator to be unitary. Its adjoint times itself is the identity, or its adjoint is equal to its inverse, if you like. So some simple examples, of course, the identity operator, this X gate, or the NOT gate, if you think about how it acts on this basis of 0, 1. And then, so these are kind of classical operations because they just sort of fix the basis. But then, of course, we also have this, this Hadamard gate. And the Hadamard gate is one we'll be using kind of over and over again. So let me just write down explicitly how it acts on the basis. So it maps ket 0 to this plus state. Okay, so it's an equally weighted superposition, we'll say, of ket 0 and ket 1. And it maps the 1 state to also an equally weighted superposition, but with where there's a minus in front of ket 1. And at this point, I just want to point out that, as theoretical computer scientists, surely you've thought about, the Fourier transform on Z mod 2 before, and you'll notice that this is exactly what this is, right? So, maybe let me just say it in words. If we think about the group Z mod 2 acting on the bit, via XOR, then these are exactly the two operations that it applies, right? The identity operator acts like the identity on the bit, and the non-identity operator swaps the two values of the bit. And the simultaneous eigenvectors of this action are exactly these two vectors. Okay, so this Hadamard gate allows us to access this dual, this sort of Fourier basis of the qubit. And that'll be kind of very important later on. Sorry. So another valid transformation that's allowed is measuring the qubit. Okay, so if we measure this this qubit here, what we're going to get is we're going to get one of the basis states, so a classical bit value, and which one we'll get is just going to be the determined by this probability distribution. The probability that we observe, ket 0 will be alpha 0 squared, and likewise for 1. Okay. And that's, of course, a valid probability distribution by this property here. Okay, so I should add, if you have questions, feel free to interrupt me. You might have to use Chris for that. Okay, so now let me quickly remind you about tensor products, because we'll need those to kind of assemble our qubits together to build larger quantum computational devices. So recall that there's this operation where, if you take two vectors from different vector spaces, you can put them together using the tensor product. And if you want to kind of write this out, in a basis, let's say for the states of two qubits, then this is exactly what it will look like. And you should, remind yourself that this is a bilinear operation, right? So here I wrote out what it means for it to be linear in the second factor, but it's also, of course, linear in the first. And where does this vector live? Well, it lives in the tensor product of the ambient spaces of the two vectors. Okay, so how do we define that? Sorry, my pointer here is a little wonky. So there are nice ways to do that. We'll do it in the ugly way. Let's pick a basis for the two spaces. So a basis Vj for capital V and a basis Wk for capital W. Then the vector space V tensor W, is the vector space whose basis is pairwise tensor products of the basis elements. Okay. This obviously means that the tensor product space, the dimension of the tensor product space will be the product of the dimensions of the factor spaces. And finally, what we'll need is some way to put together linear operators acting on the different, qubits. And that's also a tensor product. So if you have a linear operator acting on V and a linear operator acting on W, you can define, their tensor product, which acts on V tensor W, just by acting on the individual factors. And, if you, again, want to sort of write things out in a basis to see how this works, then it looks exactly like this. Okay, so if S is 2 by 2, then its tensor product with T is just this block matrix. Okay. Okay, so now that we can kind of use tensor products to build up bigger systems, we can maybe kind of take a step back and take a high-level comparison of classical and quantum computation. And here, for this, so it's going to be so high level that a classical computer for me will just be something whose states are bit strings of length n, and whose valid transformations are just arbitrary functions on n bits. Okay, and whoops, sorry, these buttons here are a little small on this device, so sometimes I miss. So, already here, there's going to be some differences between classical and quantum. So, for instance, I now want to distinguish between two classes of states, input and output states and internal states. So classically, these are the same. Quantumly, for now, I'm going to assume that I'm going to take classical strings to be my input and output states, whereas my internal states are now going to be essentially vectors composed by in vectors living in the n-fold tensor product of a single qubit. Okay, so these are now vectors, in a 2 to the n dimensional complex vector space, having norm 1. Okay, so inputs are still classical, outputs are still classical, but during computation, the quantum computer is allowed to kind of access this much larger state space. Okay, and this in some way, you should think about corresponds to the fact that while internally our quantum computers are allowed to do all sorts of stuff, when we set them up and when they kind of report results to us, because we're classical human beings, we're still going to have to use classical strings to do that. And you might remember from the qubit that also for transformations, we have to kind of have two classes. We have to have valid internal transformations, which will be unitary operators, now just acting on a much bigger space. So linear operators preserving the norm. And we're also going to have a readout, a valid kind of readout transformation, which will just be this measurement. Okay, so this is just a generalization of what was happening on the qubit. The probability of measuring some classical bit string x, conditioned on the internal state of our quantum computer being ket phi, is just the amplitude squared of that bit string in that state. Okay. And this sort of silly, kind of very high level view is enough at least to start talking about unbounded algorithms. Okay. So any questions at this point? Please feel free to interrupt. Okay, so we can talk about unbounded algorithms now. Let's take, before seeing examples, let me take one more step, which is give you a sense of how we talk about time complexity. Right, so we can do space so far because we can count qubits, but we can't do time complexity. So let's do that. So the way that we're going to do that is using a gate model, and our starting point will be, the classical circuit model, but just with a twist. The twist is that we're going to require all the circuits to be reversible ones. Okay, so implementing permutations. And just to get really specific, we're even going to ask that we use a particular gate set, namely the one consisting of the Toffoli gate. Okay, so controlled not. And this gate is universal in a certain sense for reversible classical circuits. Okay, so I claim this model of reversible classical circuits is equivalent to the standard circuit model that you're used to working with. So let me just kind of tell you in pictures how that looks. So we're going to start, so suppose you start with some arbitrary circuit for some function, let's say from 3 bits to 2 bits. And the first thing I'm going to do is notice that whatever gate set this circuit is specified in, each of these gates is a constant size object, which means that, I can write down a constant size reversible circuit using Toffoli gates for that particular gate. And that means that I can do kind of a gate by gate expansion of this circuit into a reversible circuit, which will still compute the function kind of on the top input and output wires, but it'll need some extra stuff, like maybe it'll need some extra ancillas prepared in fixed states. And it'll also produce some X-dependent garbage over here. Okay. But that's okay, because now I can do kind of another transformation where, sorry, 1 second here. My pointer is sort of not so good, but that's all right. Right, so here's what I can do to kind of make sure that there's no garbage at least, and to actually reset my ancillas to the initial state. I'm just going to add some extra wires, which will serve as the output register. I'm going to apply this CF circuit first. Then I'm going to copy the outputs to this extra register, and then I'm going to undo CF. So this will have the effect of implementing what I'm going to call UF, this map from XY to XY XOR f of X. This is now clearly a permutation. It's a reversible circuit from implementing this original function f, and it has the property that kind of whatever ancillas we used, we kind of put them back in the state that they started in. Okay. So all this work, just to get the classical reversible circuit model. Now, just to get quantum, we're actually just going to add 2 more gates, which will be this Hadamard gate that we talked about at the beginning, and this sort of measurement gate, which just means, measure the qubit that's on this wire. Okay, so Toffoli, Hadamard, and the measurement gate. And that's already enough to have actually a universal model of quantum computation. Now, of course, I promised that we would be allowed to apply arbitrary unitaries on these complex vector spaces, and you've probably already noticed that I haven't given you anything imaginary yet. So if you actually want to explore the full sort of unitary space, you need some other gates. But as far as like the computational expressivity, as from classical inputs to classical outputs, this Toffoli, Hadamard, and measurement gate set is enough. Okay. So this is kind of the model that we're gonna use. So let me jump into some examples, unless there are questions, and you should interrupt me if there are. So some simple examples. Let's just take 2 qubits and apply Hadamard gates to them. So here I'm going to already start eliminating some notation. So really, there should be like tensor products in between these things. But just like regular multiplication, I'm going to start suppressing those right away. So our initial states are ket 0, ket 0. Each of them becomes a plus. Here's what they are by definition. And now we use bilinearity to expand it out. Okay, and so notice that every classical 2-bit value appears with equal amplitude. Whoops. And then the n-qubit version of the same thing, it's easy to check, is just this uniform superposition state. So an equally weighted superposition of all the bit strings. Okay, so here's another really simple example. Start in the 0 state for both qubits, apply Hadamard to 1, and then do a C0. Okay, I haven't technically given myself a C0, but okay, fine. You can build it out of Toffoli with a fixed ancilla. So let's assume we have it. And then, this is easy. Ket 0 maps to ket, plus and 0. And then again, by bilinearity, that's just this state, okay, which is an EPR pair. It's an entangled state between these 2 qubits. And entangled is just kind of a word that for now you can just take to mean that reflect the fact that if you measure one of these qubits, then this immediately determines the value of the other, right? If I know that this one is 0, then of course the first one also has to be 0. The n-qubit version of this, and by n-qubits, I mean, if like I replace this qubit with n-qubits and this one with n-qubits, is going to be this state, and this is the maximally entangled state between 2 n-qubit systems. Okay, and this one also has this feature that if I happen to measure the first n-qubits, let's say, and I get some particular bit string, then I know that the other n-qubits will be in exactly that same classical state. Okay. So let's do another example, maybe a little bit more involved. Let's take this UF operator mapping xy to xy XOR f of x, and I've already kind of written it here in kind of quantum notation. And why am I allowed to do this? Well, basically because this is a permutation. In particular, that means it's a unitary operator. Of course, as a permutation, it just permutes basis elements around, but of course, that's a perfectly valid linear operator. And of course, it's unitary because it just permutes the basis around. That certainly doesn't change the norm. And so it's a valid quantum operation, and so it's allowed by my model. And of course, I've also allowed myself Hadamard gates, so I can write down this kind of circuit here. So let's see what that does. So I guess it maps ket x, ket 1 to ket x and ket minus, right? That's just this first Hadamard. So writing that out, that's just the state. And UF just acts on the basis. So we're going to get x f of x minus x 1 XOR f of x. And then, I guess it's easy to see that, if f of x is 0, then this is 0 minus 1, so the minus state. And if it's 1, then it's, 1 minus 0, which is minus the minus state. So this is what we get. Okay. And right, so I can just rewrite this as this, minus 1 to the f of x, ket x minus, and then this last Hadamard is just going to reset the qubit back to where it was. And so this is sometimes called phase kickback. And you'll often see, probably later in some of the talks, people using this particular form of the oracle as opposed to this one. And I'll talk about that in a second. So let's call that VF. Okay, this map that computes the function into the phase. And let me just note that if f has this particular structure, that it's a delta function. Okay, but I mean, it's true generally, but let's just take for the moment that f is a delta function, then this VF is actually a reflection operator. Okay, and here this object, which I guess we haven't seen before, is the outer product of the vector S with itself, which in the sort of usual linear algebra picture just means, the column vector S times the row vector S bar, or which of course is a matrix, and in particular is a projector onto S. And you can just very quickly compute to check that this is a valid expression for VF, right? If we just apply this to ket X, apply linearity, then we notice that this is now an inner product of S with X, so that if X is equal to S, then we get X minus 2X, and if it's not, then we just get this X. So it is indeed another expression for VF. Okay. So okay, so now let's talk about Oracle algorithms before we move to do some more examples. And here I'm going to talk about quantum algorithms, but with Oracle access to classical functions. Of course, you could imagine oracles that are also unitary, but kind of let's leave that for another time. And the way that I'm going to do oracles is I'm just going to add to the model by allowing access to this additional unitary UF, right? Which maps, ket X, ket Y to ket X, ket YX or F of X. Okay, which we already talked about, the fact that this is a perfectly valid unitary for any classical function F. So now what we can show without too much work is that without loss of generality, any quantum algorithm with access to this oracle, with the ability to kind of black box apply this unitary to their internal state, looks like the following. So we're going to prepare some state. So these are going to be 2 registers of qubits where the oracle is going to be applied, and this is just some additional memory register. And then the algorithm is allowed to prepare some arbitrary initial state. So we're going to reflect that by just saying, well, you can apply whatever unitary you like to start. Now you're going to apply the oracle on these 2 registers, and now you can decide to either go back and apply some other unitary if you like, or you can stop and measure all the qubits and output everything you have. Okay. And pictorially, this looks like this. Okay, so you prepare your fixed initial state, I guess using this first unitary operator. Now you apply the oracle, then some other unitary, and so on. And you do this, as many times as you like, and then you end with a measurement on all the qubits. Okay. So why is this without loss of generality? I mean, it's not too hard to see. I guess maybe the only kind of tricky part is, I mean, one thing that I haven't yet allowed in the model is kind of doing some measurements at intermediate stages. So because of that, it's actually not hard at all to see that this is without loss of generality. If you allow intermediate measurements, then you have to do some work to show that actually one can postpone it to the end, but let's not worry about that right now. Okay. Great. So any questions? Are there any questions, Chris? Can I just make sure that the world is still out there, and you guys can all hear me and everything?
Yes, we can hear you. And let me encourage our participants that have grown in numbers since you started.
Okay.
That it would be great if you can ask questions. Like whenever you can follow, just interrupt.
Yeah.
Are there any questions right now? Okay. Even for us. Okay. So for now, there's seem to be no questions, Corian.
Okay, great. I mean, not great, but that's okay. We'll work with that. So let me see, I keep losing my pointer here, but I can do it like this. Yeah, so let me just point out that, because we talked about this, a kind of transformation between UF and this VF operator, we could have just as well described this model of quantum algorithms with Oracle access to classical functions by granting the quantum algorithm this VF operator instead. Okay. After all, it only differs from the UF operator by a basis change on some subregisters. And this basis change can, of course, just be absorbed into the unitaries of the actual algorithm, right? So that things cancel out and you get exactly the same overall unitary being applied. Okay, so those two things are equivalent. Okay, so let's do our first kind of serious example. Let's do Grover search. So so what's the problem? The problem is we have Oracle access to some function from n bits to 1 bit, and we're promised that there's some secret input s where the function takes the value 1 and it's 0 everywhere else. Okay, and then recall this uniform superposition state, we'll need that. So here's how Grover works. So we're going to use two unitary operators. We're going to use, I'll call it U sub s now, but you'll recognize this as VF. And remember, we can get this operator from the Oracle. And then I'm going to use this reflection, I guess, across the uniform superposition state, which you can also write down with an efficient circuit, but maybe don't worry about that right now. Just recognize that it's some fixed unitary operator, and so it's allowed by our model if we ignore time complexity. Okay, so here's what we're going to do. So we're going to start in the uniform superposition state, and then we're just going to repeatedly apply these two linear operators. We're first going to apply the US reflection, and then we're going to apply minus the uniform superposition reflection, and we're just going to apply this some number of times. Okay, so this is just like in the previous slide, we just repeat this. In fact, it's even simpler because the non-Oracle unitary is just a fixed one. It doesn't change with time. And then we're just going to measure and output the result. Okay, so geometrically it looks something like this. Because we're reflecting in there's just kind of two relevant vectors that are happening. So this is in some two-dimensional space. They're not exactly orthogonal, right? Because the uniform superposition has a little bit of projection into S. It includes S. But they're kind of almost orthogonal. And then kind of if you think about it, then these two reflections act like this. And what does that mean? That means that these two reflections composed give us a rotation in this plane. And just applying this rotation over and over again, we'll kind of slowly be rotating our initial state, this uniform superposition, kind of up towards S. And now you have to do a little bit of analysis, which of course I'm not going to do here, but it's not a difficult computation to see that the rotation angle here is 2 over square root of 2 to the n. Okay, and we want a rotation by pi over 2. So if we apply this like pi over 4 times root 2 to the n times, we're going to get approximately to where we want to go. So that, if we measure, then, remembering the way that measurement is defined with high probability, we're going to actually get this ket S. And of course, this is, this is quite impressive because classically we need like 2 to the n queries to do this. Okay. So that's interesting.
Brian, there's a question.
Yes.
So F is a delta function. Now, how does that map to like the formulation that I know is like where you can find a specific output or input that gives you a specific output of any function? How is that?
So the question is, did you understand it, Corian?
No, please repeat.
Okay. Yeah, so the question is, here F is a delta function that's 0 everywhere and 1 in a particular point. The question is how to translate this into a general search problem where you search for a particular value of a function. Great
question. So I'll give sort of an example like this in a little bit, but basically the idea is to take your Oracle and compose. I mean, notice that I gave a prescription earlier for turning any function into a reversible implementation of that function. And so, one thing we can do is we can compose these things, right? So if you have your favorite function, whatever it is, and you know which thing you're aiming for, then you can, compose some circuits to write down an Oracle that actually looks like this Oracle, right? Which will be something like compute your function, check if the output is the right thing. If it is output 1, if not output 0, right? But then done reversibly so that it's actually, this of the form, UF, which is what this needs. Okay.
Thanks.
Right, good question. So, okay, so let me go on to a kind of a very different example, and that's Simon's problem. Okay, so here's Simon's problem. So now we have a oracle. It's still an oracle problem with a classical an oracle for a classical function now on n bits, from n bits to n bits, and this function is promised to be 2 to 1 in a very special way. Two function values are equal if and only if the inputs differ by some fixed string. Let's call it k. Okay, and the goal is to find k. So here's the circuit we're going to use. So we prepare 2 n qubits all in the 0 state, then we apply Hadamards to the first n qubits, we apply UF, Hadamards again on the first n qubits, and then we measure everything. Okay. So let me now point out that this transformation here, applying Hadamard to n qubits, has the following action on the basis. Okay, so this is kind of an easy computation. So if the input is a basis element ket x, then the output is this superposition, equally weighted superposition over all y with these phases -1 to the x dot y. Okay, and again here you'll recognize the z mod 2 to the n Fourier transform, and so we can kind of reasonably label these states as x hats. Okay. So now let's actually compute what happens here. So right, so we start in the 0 state, we form this uniform superposition, right? That's what happens when you apply the quantum Fourier transform on the 0 state, and then we evaluate the function, right? So then this is the state we have. And now let me just rewrite this as in a slightly different way. So instead of writing it as a superposition over inputs, I want to write it as a superposition over outputs. Okay, I mean, I can do that. It's just, re-indexing things. And, any particular output will now be associated, because this is a 2 to 1 function, with 2 preimages, I guess, which I wrote in this kind of clumsy way. But you can just ignore that notation and notice that whatever this thing is, it looks like some x and x XOR k, right, by this property up here. Okay, so if you look at the circuit, I'm going to measure this thing, and ignore that for the moment, and let's look at what happens when I Fourier transform a state like this and then measure that. Okay, so take a state like that. So I'm kind of doing this part of the circuit now. I Fourier transform this, and then by the definition of the Fourier transform, I'm going to get this state. Right, I'm just applying it here and here. And now, again, kind of a little bit of arithmetic, and you can see that what this state actually is a uniform superposition over all n-bit strings y, which are orthogonal to k. Okay. So what is the output of this procedure up here in the top? I mean, the bottom is just some random value of the function. I don't care about that. I mean, I could already get those. The first n bits will actually be producing a uniformly random y, which is orthogonal to k. Okay, and so just by linear algebra, repeating this some linear number of times will actually yield k. And this, I guess, is particularly impressive because this used a linear number of queries, and classically we need like 2 to the n over 2 queries. For a worst case f, or even for a random f with this property. Okay. This is kind of a very different algorithm, both in the sense that it uses kind of different features of, in a sense, different features of quantum mechanics, but also in that it's now an exponential speedup. of course, it did require this kind of much more specific symmetry condition on the function. Okay. So let me just kind of briefly tell you what else is out there for those who are not familiar with it. You know, there's lots of other quantum algorithms out there. You know, even if we just restrict ourselves to ones which are potentially interesting to cryptographers. So for example, there's multi-target search with for marked elements with root m over 2 to the n queries. There's collision finding with 2 to the n over 3 instead of 2 to the n over 2 queries. This is this BHT algorithm, and many other kind of polynomial speedups using this idea of amplitude amplification, which is you already kind of saw an example of that with Grover. So that's kind of in the direction of kind of Grover-like quantum speedups. The other direction is kind of following along the ideas of Simon's algorithm, which has more to do with this kind of symmetry finding property or sort of ability based on the quantum Fourier transform. And if we look, for example, at Fourier transform over other groups, like large cyclic groups, so we can also construct efficient quantum circuits for those Fourier transforms, and these yield us speedups for exponential speedups for example, finding exponentially large periods in the oracle function, and then that together with several other important ideas and a particular instantiation of this periodic f, so kind of no longer an oracle problem. We actually get the Shor's algorithm from this. And yeah.
One second, there's a question.
Comment on the quantum memory aspect of the
so the question is, how about basically the space complexity, the quantum memory required for Grover's algorithm and Simon's algorithm?
Yeah, so so for Grover's algorithm, I mean the space, the space that we used was just the n qubits that we were using to rotate in that space, right? So we just use, I mean, it was like the number of bits of input bits of the function. And so, so that's linear. For Simon, the function had n inputs, n bit inputs, right? And we needed 2 n qubits. And I guess with every run of Simon's, we can just reuse those n qubits. So it's also, it's also linear.
Okay, thanks.
Now, right. Now, of course, we should be careful here because we're talking about oracle algorithms here, right? Like if you go and you implement, if you want to implement these things, I mean, we'll talk about this a little bit in a second too. If you want to go implement these things for a specific function, now there's lots of other questions, like how much space do you need to compute that function reversibly, right? And that will, of course, affect the space complexity. Okay. Yeah, so, and there's lots of other algorithms, which I'm not going to get into, like quantum walks, quantum simulation, and lots of other things. So maybe just a kind of a slide of backing up and kind of trying to think about what's going on, and is this all okay? Is this all fair? Should we really be even be thinking about, especially in crypto, about future adversaries that can do all this stuff? And I guess maybe there's kind of two questions here. One is, is quantum computation kind of even a thing that's possible? I mean, I'm not going to really get into this one. I would just say it seems like it is, although we should be clear that devices that are capable of these algorithms that I'm describing at cryptographically relevant sizes are still quite far away. Now, maybe a more kind of a more salient question for theoretical cryptographers might be whether it was fair to grant access to this UF oracle. So let's talk about that. So here, I think the answer is that it depends, and we should distinguish between two different cases here. So One case is one where the adversary knows a circuit for this classical function f. Okay. And in that case, I think the answer is a clear yes. We should definitely consider adversaries who have access to UF. And the reason is we already talked about it basically, right? We described this, and we sketched this classical algorithm which converts, very efficient algorithm which converts classical circuits for F into this, into a reversible and hence quantum circuit for UF. Okay, so in that setting, we should definitely assume that the adversary can, of course, run this locally and then locally implement UF on their quantum computer. And so, just as an example of this, it's fair then to think that adversaries can use Grover search to find preimages of, let's say, SHA-3 hashes. Okay. Now, what about the case where the adversary does not know the full circuit for F? Well, then I claim, one needs some justification. In fact, probably the answer here is no. They should not be granted access to UF. Why is that? Well, because, there's no plausible mechanism for doing that, right? Like this algorithm is certainly no longer applicable because, some part of the circuit for F is unknown. And at least that I know of, there isn't really a physical mechanism for making a classical device that computes some function become a quantum device that implements that same function in a reversible way. In fact, I think from a kind of engineering standpoint, even just taking a classical device, a hot classical device which irreversibly computes the function f and turning into one which does it reversibly is already, if you don't know the function, is already seems pretty challenging. So just to give an example of where of such a setting, consider the Evan-Mansour cipher, and it's an easy observation that if you take the cipher and XOR it with the public permutation that's used to construct the cipher, then you get a function that essentially satisfies Simon's promise, and then you can and then if you have access to the quantum oracle, then you can run key recovery and compute the key. Okay, so maybe that's a case where access to this UF was maybe unfair. Okay. So maybe the takeaway is one should think carefully about whether adversaries should get that kind of access or not in their particular application. Yeah, go ahead. Sorry.
I was just wondering what the upper bounds of the circuit size blow up from going from classical to reversible.
So the question is, what is the upper bound on the overhead when you transform an arbitrary circuit into a reversible circuit?
I think if you allow, well, it depends a little bit on what model you're talking about. If you allow kind of non-local, not local gates, which I'm assuming we are, then I think it's a constant factor overhead. So I think, yeah, I think the circuit blows up by a constant factor.
Yeah, because you might in the worst case have a auxiliary qubit for every gate of the circuit.
So a remark from the audience is that the memory might blow up by more than a constant factor.
Why is that?
Because you might have to add an ancilla for every gate.
Oh, I'm not allowed to reuse my ancillas for gates?
Maybe, but only if you can uncompute them. So, I mean, I'm not sure whether it can be compressed more, but at least the naive approach would leave you with all the ancillas until you uncompute them at the end. Optimizations might exist, but I don't know if they exist in general.
Yeah, so it seems like in general, you might not be able to uncompute the ancillas before the end.
Right, yeah. I could tell that was Dominic, but I couldn't tell what he was saying.
Right.
But yeah, that's a fair point. Yeah. And so, right. Good. Okay. So let's go on because I think I'm a little bit behind. Okay, so the discussion on the previous slide, I think, motivates well the so-called quantum random oracle model. So, I don't need to tell you, I guess, guys, about the random oracle model. This is the model where we imagine that a uniformly random function is sampled kind of at the beginning of time, and then all parties get a black box oracle for it, which, and certainly, in the real world, if f is actually going to be a hash function, then certainly all parties can locally implement this hash function and plug whatever they like in and then get outputs back out. Okay, and then there's lots of good reasons to work in the random oracle model, provided you keep in mind some important limitations. The quantum random oracle model just adds an additional condition. It says that all parties with quantum computers should also get an oracle for the UF unitary. Okay, so still a random function is sampled at the beginning of time. Still, all classical parties get this input-output classical oracle for F, but any parties who have quantum computers should also get oracle access to UF. And why is that fair? Well, basically, we already talked about why it's fair, right? If capital F is supposed to model a public hash function, then certainly one thing that parties with quantum computers can do is implement this UF unitary locally. Okay, so we should grant them that power. Unfortunately, or maybe fortunately, depending on your point of view, security in the QROM is generally harder to establish. And you'll see some talks about that, I think. Okay. So kind of in the last few minutes, let me talk about some additional things that quantum algorithms can do, and then maybe another formalism for thinking about them. So one thing that certainly is allowed by the gate model that I described is applying a gate, applying a measurement gate and then continuing to compute. Okay. So let's look at this circuit here. So we're going to start in the 0 state on 2 qubits. We're going to apply Hadamards. Then we're going to measure one of them, which of course collapses it to a random classical bit. And then we're going to apply a C0. Okay. And so what will happen? Well, with probability half, we'll have this EPR pair, and with probability half, we'll have this different entangled state. Okay. So no big deal. We can deal with that. Partial measurement, we can also do that too. We can measure some of the qubits, and if we kind of carefully set things up, we can get some interesting states on the remaining qubits by doing that. So let's look at this circuit. So we're going to form a uniform superposition on the first n qubits. Then we're going to kind of C0 their values into the last qubit, and then we're going to measure that. So this just forms a uniform superposition, computes the parity function into the last qubit. And now when we measure, we'll collapse to either a uniform superposition over all even parity strings or a uniform superposition over all odd parity strings, each with probability half. Okay, so these are all valid things that one can do, and I'm sure you can come up with lots of other examples. Much more generally, we're allowed to apply what's called an arbitrary projective measurement. And this is specified by just selecting some collection of projectors which sum to the identity. Okay, on whatever space you're working on, let's say on the space of n qubits. And what does this applying this measurement do? So it takes a R stat or any state ket phi, and it basically what it does is it looks at how this state is sort of spread out between the various images of these projection operators, and it projects it into one of them, and then normalizes. Which subspace will it appear in? Well, that depends. That's defined by a probability distribution, which is the distribution defined by what is the norm squared projection into each of these spaces. So if it's mostly in one space, then most of the time the measurement will project to that space. If it's kind of more evenly spread out, and so on. So maybe just a quick example. The parity example here just had 2 projection operators, right? Because there were 2 possible outcomes, these 2. And this is just how you write down the corresponding projectors. Okay, so this is kind of some additional power that quantum algorithms can have. It's not really additional power. One can kind of, work with the model that I wrote down before to kind of to explain that these are also possible in it. But we should keep it in mind. Okay, so finally, in the last few minutes, which I think I still have, yeah, maybe, let me just talk about another formalism for thinking about quantum computation, which has some distinct advantages over the one that we've been using so far. So far we've been talking about what are called pure states. And notice that, we had to, in this example where we had partial measurements or kind of measurement and then continue computation, we had to talk about probability distributions on these states. And this is kind of a little bit inconvenient. So let's switch to talking about density matrices, which kind of package these things together. So we're going to replace pure states with their outer products with themselves. Okay. So these are now, so now these states are represented by matrices. And then we're going to allow you to take convex combinations of those states. Okay. Probabilistic combinations. And this is going to be, the new allowed state space. So for example, in that example that we were talking about, the way I would write the final state is, it's an equal classical, it's an equal distribution between two pure states, namely this one and this one. And so I write it as a half times the outer product of this state with itself plus a half times the outer product of this state with itself. Okay. And this is if you haven't seen this before, this is certainly not obvious, but it is a fact that this describes the same model as the model that you would get by kind of combining pure states with classical probability. And in fact, it's an axiom of quantum mechanics that two systems are perfectly indistinguishable if and only if their density matrices are equal. And here equal, I mean as linear operators. Okay, so this is maybe kind of a very important takeaway. And an important reason for cryptographers to work in the density matrix formalism, right? Because we often care about things like whether two systems are indistinguishable or not. And, at least in the case of perfect indistinguishability, just computing their density operators tells us this. So let me just do a really simple example that shows this off. Consider the following two experiments. Okay. So in the first experiment, I'm gonna flip a coin, and then depending on the value of this coin, I'm going to either prepare an output ket0 or ket1. Okay. In the other experiment, I'm also going to flip a coin, but now depending on its value, I'm either going to prepare an output the plus state or prepare an output the minus state. So a priori, these two experiments seem quite different, right? I mean, like you can do the left one on your computer. You probably can't, I don't know, unless you work at IBM or something, you can't do the second one on your computer. Very different. However, if you sit down and you compute the density matrix or density operator, right? This is where I'm going to switch to saying density operator, because we said, what we care about is equality as linear operators. The density operator for both of them is actually the identity, the normalized identity. Okay. So the maximally mixed state or the classical uniform distribution. And so by our axiom, that tells us that actually the output of these two systems is perfectly indistinguishable. There is no quantum or classical process that could possibly distinguish these two things, no matter how long it runs or how clever it is. So that's kind of interesting, and I would say not obvious in the pure state point of view. So kind of another thing that the density matrix picture or the density operator picture has going for it. And as an exercise, you might think about what would have happened if we had also output this bit B. There's a kind of a basis independent way to describe density operators as non-negative self-adjoint trace one operators, in the right space. Transformations, we can do the same transformations that we did on pure states. So unitary operators now act by conjugation. Measurements act like this. Okay, so density operator rho is mapped to the sum over all the projectors of pi j rho pi j. You can also write it this way. You know, that this is the projected and normalized state, which occurs with this probability. And it's easy to check that these are the same, right? These two things are going to cancel if you form the density matrix corresponding to this, but you shouldn't do this, right? I mean, you did all this work to get into the density matrix picture. You should stay in the density matrix picture. You shouldn't now be like mixing things, but you know. Also valid, and this is important, I think, also sometimes for cryptographers, is the fact that when we perform a measurement, really there are kind of two products of that measurement. One is the post-measurement state, and the other one is the measurement outcome, which is like a label of what projector was observed. And this is, well, this is really important because, you know, this is how humans interact with quantum experiments, right? Like we don't know what's happening inside the thing, but we do have some, you know, lights going off telling us, so, you know, like a photon was detected here and not here. And that's what this additional register, which records the measurement outcome, corresponds to. Okay. And of course, one can arbitrarily compose these things to get, you know, arbitrary quantum operations. So I think I'm kind of out of time, but let me just put up a slide, the last slide here, which is about distance measures, and just say a word or two about it. Certainly everybody's familiar with probability distribution, with, I'm sorry, total variation distance and on probability distributions. Since pure states are, you know, we could certainly also talk about the two-norm distance, but the right picture for talking about general quantum states is density operators, and there the trace distance is the right thing. This is maybe the most accessible definition here. It's a half times the trace of the absolute difference between rho and sigma. And I really, you know, this is another kind of very important takeaway fact that you should try to understand if you haven't seen it before. It says that it says in a certain sense that trace distance is the right measure for distinguishability of quantum states, right? It says that it's the maximum kind of observable distinguishability between these states, because it's the maximum total variation distance between the probability distributions that you get by measuring these two states in whatever way you like, and then looking at what the outcome is. And it's in fact equal to that max. So it also tells you that, you know, if two states have trace distance epsilon, then there is actually, in fact, a measurement which will distinguish them with that total variation distance. Okay. So sorry, this was just, you know, it's like a fire hose, but hopefully kind of, at least for some of you, you're a little more prepared for the upcoming talks. And let me stop there. Thanks.
Thanks a lot for this talk. I think we will just take the liberty of allowing 5 minutes of questions and then going, I guess, 10 minutes into the break. So there's a question over here.
Yeah. So this last part says that there exists a measurement which distinguishes it. There is some non-zero distance. But is this measurement efficient?
Okay. So the question is, this last fact is, or like one direction of the last fact is the existence of a measurement that distinguishes with an advantage given by the trace distance. But the question is it efficient to implement this measurement?
In general, no. I mean, usually no, right?
Yeah. I think now it's time to thank Gorjan again for this great introductory lecture.